India.
Nice to meet you. Where in
I'm
India are you from?
I'm from Karnataka in India.
Uh-huh.
Uh, yeah, and I'm a computer science fourth year grad student right now here, undergrad student.
Hmm.
And yeah, it is really nice to meet you.
Nice to meet you too.
It's really nice to meet you all. I think we're just live now. Could you confirm for me, Nidhi, if the stream is working?
Yes, yes,
Lovely,
yes.
fantastic. So it's great to meet you all. We have an incredible speaker lined up for you today. Her name is Clara Nellist, and I am going to introduce her a bit more to you. But first, I think you might see a very curious background both behind her camera and also on her slide. This
Mhm.
is an incredibly huge scientific facility. And maybe you know what type of facility this is, or what type of scientific experiment we have on the slide. So if we could start off with someone chiming in and saying what you see in front of you, maybe where it's located, which country,
Mm.
and if any answers come in, Nidhi, could you let us know?
Yes, yes.
Does anyone recognize this huge tube filled with very powerful magnets that accelerate very tiny things into ridiculously huge speeds? Okay, I think I see the right answer pop up a couple times. So, of course, it's the Large Hadron Collider at CERN. This is an incredible place that the lady you see right here had a huge contribution to. But to maybe show some of you what it actually is, if you're not familiar with it yet, which you definitely should be, I wanted to give you a quick intro to how people discover what parts the world is actually made of. You might have seen that whenever you want to find the most indivisible, or the smaller or the smallest particle in the known universe, you would basically try and have big things and create smaller things from them. So people for a very very long time have been trying to figure out what the universe is made out of, and the easiest way they did that is they had two elements, for example two stones, and they kept banging them together. So if you have a big stone, you can then collide it with another stone and see smaller stones arising. This is actually something that the scientists are still doing at the most incredible research facilities in the world, but on larger and then at the same time smaller scales. And they are looking at what these stones create or what elements emerge from the collisions of stones to analyze their pathways and see what the collision presented. This, in a very small overview, is what the scientists are doing at CERN. And I wanted to introduce an incredible scientist, Clara Nellist, who is going to tell you a bit more about what scientists are colliding now, because these are not stones anymore, how they're doing it, and what they're searching for. She is not only a scientist, but also a stand up comic. She might tell you a bit more about this. She speaks at numerous conferences. She is also an influencer with more than 250,000 followers on Instagram. So if you haven't heard about her before, definitely give her a follow. Particle Clara is the handle. She is a scientist with incredible experiences, but also, as I hope you're going to see, a very approachable person. So I wanted to hand it off to Clara. Thank you so much for being with us.
Thank you for the lovely introduction. Yeah, I'm Clara, and yeah, my job is to smash things together for a living and find out what they are made of on the smallest scales. So we're going to go through that today in the presentation. If there's anything that's unclear, or if I say something that you don't understand, please, I think as was said at the beginning, put questions in. I'm very happy to answer questions at the end of the presentation. So let me just reset my timer so I know where I am. My lab is called CERN, the European Organization for Nuclear Research, and it is based on the border between France and Switzerland. And it's under these beautiful mountain ranges. If you're a fan of dinosaurs, then the Jurassic region was named after these mountains at the back here. And then this lab has grown since the 1950s as we have built bigger and bigger machines in order to study our universe. And today we're talking about quantum physics, quantum everything. So I wanted to tell you about the quantum world and show you just how small we are going to go with our research. So I'm going to start this video. Hopefully it plays okay for you. So we're starting with a person, and we're going to zoom in as far as we can go, as far as we understand. So we're zooming into the hair here, and you'll see a bar at the bottom of this video. And every time we go along a tick along the bottom of the bar, we're zooming in by 10. So we're zooming in 10 times more into this video. So now we're getting into the cells. And when I said you could ask questions, you can certainly ask questions about the middle bit of this video, but I can't answer them because at the moment we're in biology, the field of biology, and that's not my scientific field. Then we're going to go into chemistry. I haven't done chemistry for a very long time, so you probably know more about chemistry than I do because I haven't studied it in a long time. But then we're going to get to my favorite field, which is physics. So we're still here looking at what the hair is made of, the materials. And now we've gotten to the elements. This is the chemistry bit. So you can see carbon and oxygen and other elements. And now we're zooming in. So this is a carbon atom. The carbon atom has electrons on the outside. So this is what we call the electron orbitals. And we're going to zoom in, and you're going to see just how far we have to zoom to now get to the very heart of those atoms. So we're still going, still going. And now we've gotten to the nucleus, which is the heart of an atom. It's made up of protons and neutrons. These are particles that are in the nucleus, but they have particles inside them too. So inside of the proton, we have quarks and then the gluons that hold them together. And this, now we are in the quantum world. I've brought you with me into the quantum world in order to study what these particles are. So let's see if I can go across. So really, we want to understand what our universe is made of. So this is now a diagram that's showing the universe over time. So it started with what we call the Big Bang. And this is when everything was incredibly hot and dense and packed together. And then very quickly, things started spreading apart out in our universe. And over time, things like galaxies and planets and stars formed. And that's what we see today. So if we want to study what our universe is made of, there are two main ways that we can do this. We can build telescopes either on Earth or send them out into space on rockets, like I have a rocket on my t-shirt. And we can look at what our universe looks like now, and also we can look back in time, because there's this really nice feature in space and in science in general, that because light takes an amount of time to travel to us, the further away things are, the further back in time we are looking. So if we send telescopes like the James Webb Space Telescope out into space, it takes pictures of our universe, and here we see thousands of galaxies just in this one image. And the further away these galaxies are, the further back in time we are looking. But we want to understand our universe throughout its whole lifetime, and there's just a point where we can't look further back in time. So what we have to do is we have to build giant machines to recreate what the universe looked like in its very early moments, to understand how the particles and the forces that control them interact together. So we build massive machines like we were talking about right at the very beginning of the live stream. This is the Large Hadron Collider, and it is the biggest machine we have ever built to do this kind of studies. And then we basically take pictures of those smashing particles together to understand what they've changed into. And then this lets us understand how our universe works on the smallest scales. Before we go into that bit, I want to tell you a little bit more about me. So this is me in front of one of our detectors. It's the experiment that I work on. It's my giant camera. And my job title is particle physicist, and I work on this ATLAS experiment. And as I said, my job is to smash things together for a living. And I studied at school physics, maths, chemistry, and English language and literature. These are the subjects I studied at the end of school. I did other subjects earlier on, but these are the ones you sort of get a certificate in at the end. And I also did film studies because I thought it was fun. And I think it's good as a scientist to try a different subjects as well, and to build up a nice round portfolio of things that we study. So then my career path after that, I did what's called an undergraduate master's degree in physics at the University of Manchester. So I studied astrophysics, so out in space, nuclear physics, how nuclear reactions happen, particle physics, that's now what I study for my job, theory, so doing all the mathematics and stuff like that. And then also I did history of science, so how did science change over time? And when I went to study in Singapore for 6 months, because I really wanted to study in a different country, I also did a bit of forensic science. So how can we use science to understand what's happened in a forensic situation? Then I went on to do a master's in, so during my master's, sorry, this is during this degree, I went to Chicago in the United States to work on one of their accelerators there. Then I got my master's degree. Then I came back to Manchester and I got my PhD in particle physics working at CERN. And then after you get a PhD, so then you can make people call you doctor if you like, I did a number of different jobs where I was a fully trained scientist, but I wanted to get more experience and I wanted to work with more people in different research labs. So I went to live in France, I went to live in Germany, and then I moved to the Netherlands, doing all of these different positions, getting different experiences and learning from other scientists so that I could build up my own skills. And then because I'd done all of those positions, I was able to apply and get an assistant professor position at the University of Amsterdam. So I now work in the Netherlands full time, but with my research in Geneva as well. And so I teach at the university as well as doing my research. And as was also said, I also do some science communication. So I love to make videos online about the work that we're doing and answer questions and show people about our research and explain particle physics. Okay, so now we're going to dive into the quantum mathematics, the quantum-ness of particle physics, and I'm going to tell you about how we do this kind of research. So this is actually the only equation I'm going to show during this whole presentation. We're not going to go into details, but this is the quantum mathematics of how our universe works on the very smallest scales. And theorists, so scientists who do the theory work over many generations, developed what we call quantum field theory, which is the rules of how our universe works. And it explains most of our universe. There's some stuff missing that I'm going to tell you about, but it's a very strong mathematical explanation. And then I have a little note at the bottom of my slide, because you may have heard, if you study quantum mechanics or anything about quantum, that you have wave particle duality. So things can be a wave and they can be a particle at the same time. So for example, the photon, the particle of light, it can behave like a wave or it can behave like a particle. Now, I'm a particle physicist, so my bias is only looking really at them when they behave particle-like. We do a little bit of the wave stuff, but mostly I'm only going to talk about them as particles in this presentation. So that maths that I showed you in the previous slide, this is what it then looks like in a more graphical form. So we have the different particles that make up our universe. These are all the building blocks. If you're a fan of something like Lego, then these are the Lego bricks that we can use to build a universe with. So the ones on your left, these are the matter particles, the stuff. They make up you and me and planets, and these are really the building blocks. And then the ones in red are the forces. They decide how these building blocks interact with each other. So the one you might be most familiar with is this electron particle. So electron is involved in electricity. And then it's got some heavier cousins that we can see on the right of it. And then these up and down quarks, those are the things that are in the center of the atoms, the nucleus of the atom. So these are really important, these three on the very left, for building atoms that you can then build a lot of other things for. Neutrinos at the bottom are super interesting, but I'm basically not going to talk about them because my research doesn't involve them too much, but they're really interesting particles. And then I'm going to tell you a little bit more about these red particles first, because these are the force carriers in the standard model. So we have the photon, which is the one you might be the most familiar with. This is the particle of light, and it's involved in electricity and magnetism, and we call it the electromagnetic spectrum. So this photon, we can go all the way from radio waves all the way down to gamma rays. So depending on the frequency, so now I am talking about waves here, but depending on the frequency of photons, that defines how we would interact with it. So that's the photon. Then we have the gluon. This is probably the best named particle we have in particle physics because it glues stuff together. It holds things together. So inside of a proton, it holds the quarks in place. And it also holds the protons and neutrons together in an atom. So that's the job of that particle. And then the W and Z bosons, these are also force particles, and they're really important for making our sun shine. So they're involved in nuclear decay, and without these particles, our sun wouldn't shine and we would not exist at all. So all of these particles have different jobs in our universe, and they do their jobs very well, and that means that we can exist, and that's a very good thing. So we have this nice recipe book of all of the particles in our universe, but there are some things missing. So there's these particles only make up 5% of our universe, so a really tiny amount of our universe. There are things that we call dark matter and dark energy that we have no idea what they are, and they're not explained by the things we've already found. And also, I was talking about forces. If you're going to know a force, the one you probably know the best is gravity. And gravity is not explained in this model at all. So that one's also missing from our recipe book. So we have these really big questions in physics, and we want to understand how, where these missing things are and how everything works together. So I'm going to tell you about the Higgs boson. I'm not sure if people will have heard of the Higgs boson, but I'm going to, yeah, perfect, excellent. So I'm going to explain the Higgs boson. So the Higgs boson tells us how we get mass in the universe. So why things are massive. And then when you're on a planet and you've got gravity, then that changes to weight. But some of that weight actually comes from a different force, but the mass from the Higgs is very important too. And basically, you can think about the mass from the Higgs boson as a property throughout the whole of the universe. So if you ever play computer games and you have a rule, a setting in your computer game, it's the same everywhere in your game. But you can, in a computer game, change that setting, and then it will change how the computer game performs or reacts. And so in the very beginning of the universe, this Higgs field was set at 0. It didn't have a setting. And then this ball rolls down into the bottom of the hill, and now we have a value for this setting, and it then defines how things have mass. So we can see this in this is our universe. So we can see this in a nice video. These are particles whizzing around the universe at the speed of light. And this is before, where's my mouse gone? There it is. This is before the Higgs boson has a setting. So you saw they were whizzing around really quickly because they didn't have any mass. And then when we turn that setting on, some of the particles interact with the Higgs field, and you see some of them slow down. Now they've got mass, now they're interacting with the Higgs field. So we have changed the rules of the universe. And this is really important because these are the very smallest rules, and then that affects us on a bigger scale. So I'm going to move to this slide because another way to explain this, I like to explain this with snow so that you can understand the Higgs field. So the Higgs field is like a field of snow, just spreading out everywhere. And how much if you were a particle, interact with the Higgs field, interact with the snow, defines how much mass you have. So if you're, and I call this a light particle, but it really should say like an electron. If you're a particle with not so much mass, then you interact with the field a little bit, but not so much. So you get a little bit of mass. So this is like the skiing you can see on the left-hand side of the image. But if you're a really massive particle, it's like you forgot your skis and now you have to trudge through the snow. I'm not sure if you've had to do this in a really deep snowfield, but it's quite tricky. And then you have a lot of inertia because now you're interacting with that field a lot. And so you have a lot more mass. And then the Higgs boson, which is the particle we were trying to look for, is the snow interacting with itself. So if the snow interacts with itself, you get a snowball. And by finding a snowball, that tells you that the field exists. And that's really important to be able to say that this theory that that was proposed is the true description of our universe. Okay, so we have the Higgs field. This was a big question. I also mentioned dark matter. So I said, if you look at this diagram, everything in our universe is only 5% of our universe. And everything else, the other 95%, is dark matter and dark energy. So we know that dark matter is out in our universe. It's this other kind of stuff that we can't see. It doesn't interact with light, but we don't know what it's made of. And the way that we discover it is that Einstein says that when there's stuff out in space, it's going to bend the path of light as it passes by. So we can look out in space and we can look at galaxies with another galaxy in front of them, and their light, you see these orange paths, is bent as it travels towards us. And so the more stuff that's in the way, the more this light is bent. And we can calculate how much stuff should have been there that interacts with light and how much stuff is there from this bending of the path. And these are different numbers. So what we've learned is that out in space, there's more stuff than we can see with light. And that's dark matter. And otherwise, we have no idea what it is. So we have these proposals of all these other types of particles that it could be, or even not particles. It could be different types of black holes, for example. But we have no idea yet, and we're still looking to try and understand what dark matter is. We also, if you've heard of antimatter, we're trying to understand where all the antimatter from the beginning of our universe went, because in the very, very early universe, we think there were equal amounts of matter and antimatter. And now there's mostly just matter, because that's what you and I are made of. And we don't know where all of the antimatter went. So it was discovered almost 100 years ago, this antimatter. This is a photograph from, I think 1932 was the year that this photograph was taken. And it's basically, it looks like an electron. So we know electrons very well, but it has a positive charge. And antimatter are just particles that look exactly the same as regular matter, but they have a different electric charge. And when they come together, if you have an electron and a positron that come together, then they annihilate and they turn into energy. And that's why we think that in the very early universe, there were equal amounts, but if there were, they would have all annihilated together. So now we're just left with a little bit of matter, and we're trying to understand why. So the one last big question is, I talked about the strength of gravity. So we think that gravity is quite a strong force. I mean, if I fall over, it hurts, and that's because gravity has pulled me down. But I can overcome the entire strength of gravity from the Earth by lifting this cup. So not with everything, there are certain weights I can't pick up, but I can overcome the force of gravity. So it's actually a very weak force. And there are theorists that are working on something called quantum gravity. They're trying to work out, is there a quantum nature of gravity that we can explain? And if so, is there a particle that explains gravity called a graviton? We're still looking for this. Are there extra dimensions in our universe that gravity could be leaking into, and that's where it's all gone? And also they want to know, we've just talked about antimatter, whether gravity interacts with antimatter in the same way that it interacts with matter. So these are all big questions in physics. So now that's the theory bit. And if you have any questions about anything I said, I'm very happy to talk about that in more detail at the end. But now I'm going to explain how we go about answering these questions, because this is what I do. I'm an experimental physicist, and I like to work on the machinery and do the data analysis and the programming and really do the hands-on data studies. So I told you already that CERN is near France and Switzerland, but we're going to have a zoom in on the planet. So this is planet Earth. Hopefully you recognize it. And now we're zooming into Europe, and we're near Geneva. So here you can see the lake near Geneva. At the bottom, we have the airport, and the accelerator. I told you it was massive, but it is 27 kilometers long. So it is the biggest particle accelerator. It's about between 16 and 17 miles long, this accelerator, and it's 100 meters underground. And then we put big experiments around the edge of it. So you can see 4 experiments here. And the way that we do these studies, so I'm going to pause it in a second. So to understand everything that I've just explained, we want to smash protons together. And protons are these subatomic particles that I was talking about earlier, and we can get them from a bottle of hydrogen. So hydrogen gas is hydrogen is a proton and an electron. So if we remove the electron, then we're left with the protons. So we feed the hydrogen gas into the machine. We then do some nice tricks where we can add extra electrons in to really improve the concentration of protons. But then we remove those electrons and we're just left with our protons. And then we feed them into what we call a linear accelerator. That went by very quickly. Let's go back. So a linear accelerator uses electromagnetic fields to be able to push these protons and accelerate them inside of the accelerator. So the best way that I think about this is if you're sitting on a swing and somebody is pushing you from behind, if they push you at just the right time, then you get higher and higher on the swing. If they push you at the wrong time, then you'll start to slow down. And so each of these pieces in the center of the linear accelerator are pushing the protons with an electromagnetic field, like a magnetic field. And if we time it just right, they get a good push and they get faster. So we're accelerating the protons in this straight line accelerator. We call it a linear accelerator. And then we start putting them in circular accelerators. And here we can start collecting the protons together, and we're making them going faster and faster in each of these accelerators here at CERN. And what we want to do is collect 100 billion protons. So the same number of protons as we have stars in our galaxy. And we want to squish them together to about the size of a human hair. And we want to speed them up to very close to the speed of light, which is the fastest we can go in the universe. So it's not quite at the speed of light, but it's almost. And then we get them into the Large Hadron Collider. They're going in opposite directions, and we smash them together. And when these protons smash together, we're using Einstein's equation E equals mc squared. It's one of the most famous equations. So I said there was only one equation, but I'm saying a second. It's one of the most famous equations that we have in physics. And it tells you that energy and matter can be changed into each other. And because of that c squared, you can take a little bit of matter, have a large amount of energy. And so we smash these protons together, they turn into energy, and then we can use them to turn into different type of particles in order to then be able to study what our universe is made of. So this is how the Large Hadron Collider works, and we do it at 4 main points around the ring. We have other experiments at CERN too, but these are the ones I'm focusing on. And something that's really exciting is that our experiment is colder than outer space. So outer space is 3 Kelvin, which is 3 degrees centigrade above absolute zero, which is 269, minus 269 degrees centigrade. I think I've done the right calculations, or minus 270. And we are 1.9 Kelvin. So we are even colder than outer space in our experiments. And that's partly because we use superconducting magnets. So these blue tubes that we saw at the very beginning, these are the magnets to keep the protons going in a circle. So we need very, very strong magnets. And to do that, we need superconducting materials. And this is a quantum phenomena. So this is also where quantum mechanics comes into our experiment. And what happens is the material in the magnet, we cool it down, and then it has no electrical resistance in it. So we can put almost 12,000 amps through these magnets, and there's no electrical resistance. And then we can have very strong magnetic fields that hold the protons going around in a circle, or keep them going around in a circle, which is really important to be able to do our measurements. And so now we're going to look at the experiments in more detail, and we're going to focus on the ATLAS experiment because that's what I work on. So hopefully this should, yeah. So we've got those protons going around, and they're whizzing around the LHC, the Large Hadron Collider, 11,000 times per second. So they go around that 27-kilometer long ring over 11,000 times per second. And then we bring them together, as you've already seen, in the center of our detectors, and we smash them together. And as I said, we're doing Einstein's equation, E equals mc squared. This is creating new particles. And the interesting particles that we want to study, they don't last for very long. So the Higgs boson, it really doesn't stick around, and it quickly changes into other types of particles. So that's that kind of firework shape you're seeing coming out of the center of the collisions. These are the other types of particles like electrons or their cousins, the muons, and they're coming out of the center of the collisions, and that's what we're measuring in our detector. And so this is happening, yeah, around 11,000 times a second, and we have to collect all of that data and work out what happened very, very quickly. So to do that, we have a detector like the ATLAS experiment. So I said you can think of it a bit like a giant camera. It's obviously more sophisticated than the ones in your phone, but it is measuring the particles as they pass through. We're getting the properties of those particles, and then we reconstruct what happens in those collisions. So it's 44 meters long, and then it's 25 meters tall. And in this original image, we had these two little people to show you just how big this detector is. I didn't think they were the best examples, so I added the dinosaur in so that you can see just how massive this detector is. And each part of the detector has a custom role. I don't really have time in this talk to tell you about each of the different jobs, but I'm happy to talk about it in more detail anytime. But what I wanted to show you is this is what the cavern looked like before we put the detector in there. So we dug a big hole in the ground around 100 meters underground, and then we wanted to put the detector in. And it's quite tricky to do that because the detector is extremely heavy. It's 7,000 tons. So you can't build it on the surface and lower it down all in one go. So what we did is we used a trick that many artistic people have been doing for hundreds of years, where if they wanted to build a ship in a glass bottle, which is this beautiful ornament, but also you look at it and you think, how did you get a ship inside that glass bottle? Well, you can add a piece in through the neck, and then you have to build it inside the bottle, which is very tricky. And we did the same thing with our detector. So we lowered the pieces one by one from the surface through these giant shafts we have to the surface. And then the detector was constructed underground from those pieces. So some of them were constructed above ground and then lowered in, and then the whole detector was built. And then we got something that looked like this. So this is a multiple pictures I took of our detector and stitched them together so that you get a sense of just how huge it is. And because it's still quite difficult to understand how big it is just from this image, I wanted to show you that these in the center are people working on the experiment. So to study the tiniest things we have in the universe, we need to build the biggest experiments that we have on Earth. So it's really complicated. And it also takes a lot of people to do this kind of research. So my experiment alone has around, the numbers vary, but between 5,000 and 6,000 people working on this experiment, with over 100 different nationalities represented in the experiment. One of my favorite things about my research, I mean, I love the physics, but what I love about working at CERN is that I can walk through the restaurant and I will hear 6, 7, 8, 9, 10 different languages all being spoken in the restaurant, different groups of people. I mean, we also, of course, mix together, but it's just really lovely to hear all of the different languages, and the fact that it takes people from all over the world to come together to do this kind of research. And so here I wanted to show you some of the pictures. This is nowhere near everybody that works at CERN, but in the bottom left, you see the Atlas experiment. I would say this isn't even 10% of the people that work on my experiment, but you can see there's loads of them. In the top left, we have the Alice experiment. The bottom right, we have CMS, which is sort of the sibling experiment to Atlas. And the top right, we have LHCb. So LHCb really loves to study antimatter. Alice really loves to study the very early universe. And Atlas and CMS, we discovered the Higgs boson, and we try and measure as much as we possibly can in our experiments. And then in the center, we see some of the people who work on the accelerators in order to make those collisions happen. But this really isn't everyone. It's just a tiny fraction. And one of the things we're very proud of at CERN is, apart from the physics, we're also the birthplace of the World Wide Web. So this is Tim Berners-Lee, and he was studying, he's a computer guy, and he proposed a way to get all those people, so not these ones, but in the 90s, all the people at CERN to be able to share their information and talk to each other. And he made a proposal for information management, and his supervisor at the time wrote on the top of his document, "Vague but exciting." And now this has changed the way that we communicate around the world. This was such a huge thing, the World Wide Web. But Tim Berners-Lee was the guy that proposed it, and then because of the way that CERN works, it was just sent out for free. So you do have to pay for the internet, but you don't have to pay to use the web, which is just one of the factors of, it's the way that CERN works. We don't patent things, we don't put things behind a paywall. Everything is shared with the world for free. So then I mentioned the Higgs boson and the discovery, and this was one of the huge successes of the Large Hadron Collider. So what we do is, this is how I look at the data that comes from the Large Hadron Collider. So we are taking the data, and here we're looking at two photons, so two particles of light, and we're measuring their energy, which we use a nice trick so that we can say it's the same as mass. That E equals mc squared. We set C to equal to 1, and then we can say energy and mass are exactly the same thing, which is super useful in physics. And so what we do is we count over time. So we collect all the data, and we count, in this case, how many photons we see and at what energies they are. And if there's a new particle, we'll see slightly more photons if it interacts directly or indirectly with the photon at a certain point than is predicted by the background, the stuff we already know about. And you can see here that we saw a little bump in 2012. And we looked in lots of other different ways, so other particles, to see if we saw the same thing. We added that all together, and then that was enough to say that we discovered a new particle, a new building block of our universe called the Higgs boson, and we had a big party at CERN. So this is something that people have been looking for over 50 years. There were 6 theorists that were directly involved in proposing this way that particles get mass. And this is a new, what we call fundamental particle. So as far as we know, we can't break it into any smaller pieces. And this is a huge achievement. So we were very happy that we discovered the Higgs boson. And yeah, we had a party at CERN. It made the front page of a lot of newspapers. And I was a student at the time. I'd only just really started working at CERN a few years before. And I was able to get in the back of that room. So that's my face. And this is on the picture of the New York Times. And I was able to witness this moment in history where we announced to the world that we discovered a new particle. And it was really special to see all the people that have been working their entire careers on this kind of research, and especially on trying to find the Higgs boson, and just the joy of people coming together to learn something new about their universe, about our universe, was really, really special. But to get into that room, I had to queue up outside. So it was a bit like a music concert if you wanted to get in. We slept outside from midnight the night before in order to be the first people in that room, because the people at the front, the really important ones that had been working on it for decades, they got reserved seats, as they should. And then there were some seats at the back that were just open for anyone. And so we got some Disney movies, we got our pillows and some popcorn, and had a little particle physics slumber party outside of the auditorium, so that we got to be there and listen to the presentations. And then this picture on the right, this person is Dr. Fabiola Gianotti. She was the head of my experiment at the time, so she was the boss of Atlas. And right now she is the boss of all of CERN. So she is the Director General of CERN and runs the entire lab of over 20,000 people doing this kind of research. So she's a really important physicist who was sort of leading the experiment when the Higgs boson was discovered, and now she leads the entire lab. So it was really inspirational to be able to sit and watch her presentation, being able to announce to the world, along with the CMS experiment, that we had discovered this new particle. So then this is the particle on the right here, the yellow one, that we were able to add into our table and improve our collection of all of the particles that we've discovered so far in what we call the standard model. It's like our recipe book. But as I said, there's still stuff missing. We don't know what dark matter is. We don't know what dark energy is. And we don't have gravity in this table, for example. So we've still got a lot of work to do. There's still a lot we need to understand. One kind of side note before I move on to the next comment is that I wanted to tell you about, because this is a quantum talk, so I want to say the word quantum as much as I possibly can. And so something we can learn is also about quantum entanglement of particles. So we know that you can have the quantum entanglement where two particles have this special connection. And even if you separate them over long distances, if you measure one particle, then you know what the other particle is going to be like, because they have this quantum interaction. But we'd never measured it at really high energies before. So we'd often measured it in sort of low energy conditions, but the Large Hadron Collider is a very highly energetic system. And so we wanted to see if particles at high energies also experience quantum entanglement. And we were able to measure between two, they're called top quarks, they're the heaviest particles we've ever discovered. And we were able to show that they had quantum entanglement too, which is a really interesting. Does quantum mechanics also work at very high energies? And this shows that it does. So this was a really nice measurement that was recently done with the Large Hadron Collider, that we're still learning about how particles work. So I'm almost, I'm going to wrap up quite soon so that we have lots of time for questions. But I want to tell you that we discovered the Higgs boson, and we're looking for things like dark matter. But it's not just about discovery with the Large Hadron Collider. It's also about what we call precision. It's about learning in as much detail that how these particles work, what their properties are, what are the rules of our universe. And this can help us find dark matter, for example. And the best sort of example I have for this, best analogy, is that this is Neptune, I think, I hope. I'm not an space physicist, but this is Neptune. And Neptune was discovered in our universe because they measured where all the other planets were in our solar system and very precisely looked at their wobble and where they should be. And then we were able to say, okay, it looks like something else is interacting with them gravitationally. And they predicted Neptune, they predicted where it should be, pointed a telescope there, and it was discovered. So really understanding the things you already know about helps you to look for new things. And that's what we do in particle physics. So this is a nice complicated plot that I don't want to panic you with, but each of these sort of like groups of dots they're not planets, but they're particle processes that you can think of like the planets. If we're measuring their properties and where they are and how they interact with each other, perhaps it can help us to look for things like dark matter. So we keep very busy with the Large Hadron Collider, measuring all of the ways that the particles interact with each other, and this can then help us to find new information as well. And yeah, I might do the next bit if we have questions, but I want to save time for that. So I just want to say, how does this affect you? So you might think this is really nice, it's very interesting, but why do we do particle physics for day-to-day reasons? And my first answer is always that learning more about our universe is just a fundamental human curiosity. I do this research because I want to know how our universe works on the smallest scales, and then that tells us how the universe works on the very biggest scales, things like galaxies and black holes and things like that. And I also very strongly think that we dance and we make music and we do art because these are just things that humans do that make us creative and humans, yeah. And that curiosity is another human trait that is just something that we should enjoy. But there's lots of cool technology that comes from the research that we do as well. So we also are able to make things like medical technology from learning about this particle physics stuff. So I very briefly mentioned antimatter, and we use antimatter in what we call PET scans. They're positron emission tomography scanners. And this allows us to look inside of the human body without having to do any surgery, which is really important. And so knowing about antimatter helps us use these scans. We also have MRIs machines, which use superconducting magnets, so like the ones in the LHC, and they rely on the quantum property of spin, so in the water in our bodies, to be able to work and look inside us as well. So there's a lot of quantum in MRI machines. And then also, of course, we hear a lot about quantum computers at the moment. And quantum computers, some of them use superconducting electronics, and so they have to be made very, very cold. So I was talking about how cold the LHC has to be kept. Quantum computers also have to be kept at very cold temperatures, and that's a very tricky thing to do. So if we were able to develop room temperature superconductors, this would be fantastic for my research because we wouldn't have to keep our magnets so cold. It would also be a game changer for things like quantum computers and also travel and other areas that would like to use superconductors at warmer temperatures. And maybe then in the future, we could have a quantum computer in every home. I remember reading things from, so I wasn't alive in the 1960s, but from like 80 years ago or something, or 60 years ago, can't do calculations, where they were talking about computers and how, computers used to fill an entire room, and now we carry them around in our pockets all the time. And so at the moment, can't talk anymore, quantum computers, they need to be cooled, they're very complicated, but perhaps with future improvements, we would be able to also carry quantum computers in our pockets, potentially, we have to see. And then quantum computers would also be very useful in particle physics for data processing. I didn't really get a chance to tell you just how much data we have in the Large Hadron Collider, but we have more data than there are videos on YouTube. So there's more data coming from the Large Hadron Collider. We can't keep it all. Than there's data on YouTube. And so for the future of particle physics, we've only collected about 10% of the data with the Large Hadron Collider so far. We've still got 90% of the data to go. So we are going to be improving our accelerator and make it even more efficient so we can collect more collisions, and then this can help us find even rarer processes. And potentially we're going to build another accelerator in the future, even bigger, even higher energies, which will help us to understand our universe in even smaller details. And before I go, I want to tell you about how you could work at CERN and some of the challenges that you could help us solve. So these huge data processing challenges require programming skills, and they're very important for being a particle physicist. Or if you're more hands-on, you like to build things, then you might like to work in a laboratory and building new detector components, so new bits of that camera I was talking about. Or if you really like mathematics, maybe you can be a theorist and work on the calculations and help come up with new suggestions of things that we want to look for in our research. And then there's so much more going on at CERN that's not just directly the physics. So we have robotics and computing, communication, like radio and electronics, vacuum and cryogenics, electrical engineering, civil engineering, mechanical engineering, material science, and so much more. We also have firefighters at CERN, so we have an entire firefighting department in our lab. And I'm going to leave this just long enough that if anybody would like to come and work at CERN, they can go back and grab the QR code from this slide and learn about the different careers that we have at CERN. And hopefully now we have enough time for questions. So thank you so much for listening to me.
We sure do. It was an absolutely incredible presentation, so thank you so much for it. What was really exciting to us is that you've actually anticipated many of the questions that our participants had while speaking, but we also have a lot more coming. I love your underlining of the fact that different disciplines need to come together in order for huge breakthroughs to come along. We also believe that at Girls on Quantum, we have a quantum arts competition coming on really soon, where our participants are going to be exploring different topics that are coming either from physics or quantum or particle science and connecting it with different media. So I wanted to ask you maybe to give them a bit of a head start or a bit of an inspiration. Do you have any either theorems or facts or things that you think are very either visually interesting or particularly interesting to you, or just cool that you'd like to share with our participants so that they can use them in a visual expression?
Oh, sure. Yeah, I mean, the things that I'm just going to whiz back in my slides. The things that I look at every day are things like this here. And we have a lot of them. And you also saw it in the video. So when these protons collide together, then we get this sort of firework shape of new particles coming off. And depending on the type of particle, it looks different. So if we get quarks, which are in the center of protons, then they always like to pair up. They don't like to be by themselves. And when they pair up and they interact with our material, they cause a jet, like a spray of particles in our detector, which leaves like a really like big chunky signature. Whereas if we get a muon, which is the cousin of the electron, it leaves like a very nice thin straight line. So I think it's really nice artistically to imagine the different particles as they come from the center of the collision. What else could I suggest? I think also the detector itself. I don't know if this matches your theme. This is accelerator, sorry, not the detector. But I think the machinery is very artistically interesting and beautiful, and could be some nice inspiration. I'm not sure if that matches what you were asking.
Of course. And one more thing about the intersections between disciplines. We also heard you talking about literally cool things, things that are really cool, both the superconducting magnets and then quantum computers. And we wanted to maybe bridge the theme of quantum because we have many quantum enthusiasts amongst ourselves. So if we have these super cold chips, let's say to 20 millikelvin, that can do a lot of operations in succession or simultaneously, could you maybe tell us what sort of troubles you are experiencing while you're doing your data processing at CERN, or what are the problems that classical computers can't solve for you at this minute? And where do you think that quantum maybe might be able to jump in and solve these issues for you?
Ah, very good. Do I have a good backup slide for this? Just having a quick whiz through to see. No. Okay. So yeah, for the quantum computing, let me put that slide up while we're talking.
We of course appreciate a plug of the Quantum Technology Institute initiative if you'd like.
Yeah, maybe you can, if there's details, maybe you can share that afterwards. But for quantum computers, we have all this data that comes from the Large Hadron Collider, and we can't possibly keep it all. And on top of that, we have to simulate. So we do digital simulations of what the theorists are predicting should be happening in those collisions, and then we compare the two. And then we update the predictions depending on the data that we receive. And then this is how we improve our understanding of how the universe works. And it's a very slow process. And some of these calculations, the mathematics that you have to do, the more precise the mathematics, the longer each single event takes to calculate. And with quantum computers, you would just be able to calculate so much more detail in one go. And we would have a much bigger collection of simulations that we can compare our data to, that we would have a much better idea of what was going on in those collisions. So that's really how quantum computers are going to help with particle physics, is processing the incredible amounts of data. It's petabytes of data that we get from the Large Hadron Collider, and then we need more than that again for the simulations to compare the different scenarios of what we think is happening with what is actually happening. So it will really be a game changer for us having quantum computers to be able to process all of this data.
So guys, keep your questions coming because we've had just a question about what Clara mentioned now about precision. Let me introduce Nidhi to you. She's one of our quantum ambassadors at Gauss and Quantum, and she's going to be moderating the Q&A session for you.
Yeah. Hello, everybody. Clara, it was an amazing session. I mean, the questions itself tells how interesting it was. All the antimatter part and everything. It's very interesting. Okay, so there are a couple of questions from Discord as well as on YouTube chat. So I'll just start from YouTube chat. So there is this question like, what are the tools that are available to observe such tiny particles, like the ones that you mentioned, like those tiny particles. So could you just answer that?
Yeah, so the tool that we use is the Atlas experiment, for example. It's one of the big experiments. And what happens is that in the collision, we have the collision come in, something is created like a Higgs boson, and then it quickly changes into other types of particles. In fact, I think I have, 1 second, this one, perfect. So I can show you this video. So I didn't keep it in due to time. But the main, we have three main sections of our detector. So we have the central section that we call the tracking detector, and it tracks charged particles as they come. So now we're looking, this is the beam pipe in the center. We're looking sort of head on to the detector. And so the tracking detector tracks charged particles. Then we have the calorimeters. And the way that I always remember this is if you think your food has calories in it, and that tells us about the energy that we get from food. And so the calorimeters are a measure of energy that we have from the particles. And then I mentioned the muons quite a lot. They're the heavier cousins of electrons, and they like to travel a long way before they even get stopped by anything. And so we have a special section of the detector just for them. And what we do is after the collision, the particles will come from the center. So now we see an electron, and each different particle leaves a different signature in the detector. So if it has an electric charge, then it will leave a track in the tracking detector. And then the electron and the photon leave energy in the electromagnetic calorimeter. Or if we have a proton, that will travel through and that gets stopped in the hadronic calorimeter because they're hadrons. Neutrons also get stopped there, but they're neutral, so they didn't leave a track. Muons pass all the way through. And then neutrinos, which I barely got to mention, we could do a whole talk just on neutrinos, are these very, very light sort of additional cousins of electrons. They're neutral particles. and they don't interact with anything in our detector. You have to detect them with giant bodies of liquid water or ice. So we have Ice Cube in Antarctica, and we have KM3 net, which is in the Mediterranean Sea, and they are kilometers of water in order to be able to measure neutrinos. So we just cannot possibly measure them in our detector. And so we use a process that we call missing momentum. So we know that when the protons come in, they collide head on. And so there's no momentum in what we call the transverse plane. The bit, if they come in this direction, there's no momentum at the beginning around them. And so if we see a lot of stuff going in one direction and there's nothing to balance it out, we know that they should be equal, then we can say that there's something missing in our detector. And if it's a little bit of missing momentum, then it's a neutrino, because we know that neutrinos are very light. This is one of the ways we look for dark matter. If there's a lot of stuff missing in one direction, we know it couldn't possibly have been carried away by a neutrino. So something massive that didn't interact with our detector should have been there. And that's how we say it could be dark matter. But so far, we haven't discovered dark matter in that way, but it's one of the ways that we look for it. So this is what we have. We have the electronics and the customized detectors in our bigger detector, and each different particle leaves a different signature. And so then we have to be like a detective and add all these up together, and we do this thousands of times a second. So we're actually doing this with it used to be done. So actually the theme of because this is a Girls in Quantum event, it used to be done when we had different kinds of detectors by taking pictures. They could actually see with a camera the tracks in what we call bubble chambers. And then women used to be the ones who would analyze these photographs, thousands of photographs, track the particles with a ruler and do the calculations and measure what the particles were. So they were called scanning girls at CERN, and it was the women that were doing the measurements and the calculations. Now we do it through algorithms, and we use a lot of also machine learning. So the algorithms that we develop to be able to reconstruct where everything has gone.
Great to know that. They were scanning girls. We are quantum and girls this
Yeah,
time.
exactly.
So the next question is there any relation between black holes and dark energy? Like, are there any research going on right now?
So not with, as far as I know, not with dark energy. So dark energy is the energy in the universe that causes the accelerated expansion of our universe. So if I whiz back to the picture from the very beginning, this is the universe over time, and it started very hot and dense and close together right after the Big Bang. And it has not only been expanding, but this expansion has been accelerating. And this is caused by dark energy. And the black holes aren't linked there, but there are some proposals that dark matter could be not supermassive black holes, but what we call primordial or microscopic black holes. So actually they're slightly different things, but microscopic black holes, which are very, very tiny concentrated black holes, but that doesn't solve all of the questions that we have that dark matter does solve. So dark matter is really important, for example, for the very early universe of how stuff clumped together, which then eventually led to galaxies. And having microscopic black holes being dark matter doesn't solve every question we have about it. So then it would still leave something that we needed. So it's not one of the leading proposals, but it has been discussed.
And there's a follow-up about dark energy, because there are many different theories, but are there any that captured your attention specifically, or that you think might be particularly revolutionary in that field?
I think the exciting thing about dark energy right now is the fact that we thought it was sort of a constant value, and the DAISY experiment has recently shown that it might have been changing over time. So this was a really recent result that came out that was very exciting, as they look at the effect of dark energy over time. But there's also, so as well as I'm mostly focused on dark matter at CERN because we're trying to see if it's a particle. There's an experiment called Euclid, which was also it's an ESA experiment that was sent out to study the dark universe. So it's taking a survey of our sky from outer space, and it's looking not only at dark matter but also at dark energy. So by taking a lot of photographs, it's going to give scientists a really good understanding of how dark matter and dark energy work out in the universe, in the cosmos, which then helps us to make better predictions. So I'm really excited for experiments like Euclid that's going to give us more precise information, and also the results that came from DAISY.
Do we have time for 2 more questions? Because there are 2 very
From
eager
me, we have all
participants
the
who want to
time in
ask
the
them.
world. So
Lovely, fantastic. So yes, there is one about antimatter, and I think
Mhm.
it's a good opportunity for you to tell our viewers a bit more about it.
Yeah.
They asked, how big is the imbalance between matter and antimatter in the world or in the universe?
Oh, that's a great question. There's basically no antimatter. I actually should know the exact number, but I don't work on it day to day, so I'd have to pull the number up. But we think it was a tiny, tiny fraction of the difference between matter and antimatter. One of my LHCb colleagues could tell you the exact number directly, but what we think is that there was almost exactly the same amounts of matter and antimatter, and then it really was like point of a difference. And so then all of the matter and antimatter annihilated except for this very tiny amount that was left over of matter, and then that's what makes up you and me and galaxies and stuff like that. So it's a really, really tiny imbalance. And this is something that especially the LHCb experiment at CERN is doing a lot of work to understand. And then also we have experiments that, did I show you this one or did I? No, I jumped over this. So we actually have an antimatter factory at CERN, which is the best named building we have at CERN. And here we have a decelerator. So we have accelerators at CERN and we have a decelerator, and we can create antiprotons and anti-electrons, so positrons, and we can create anti-atoms and study antimatter in really precise detail. And one of the things they were trying to understand is, does antimatter interact with gravity the same way that matter, or does matter attract antimatter with gravity the same way that matter and matter attract? And so they can create, they take the antiprotons and the anti-electrons, create an anti-atom, and then they release them in the experiments. And you would expect as a gas, things just sort of to float away from each other. But if gravity is having an effect, that gas will also fall a bit. And they can then measure from the annihilation. So when matter and antimatter come together, they annihilate, where these anti-atoms have gone and whether or not the strength of gravity is the same. And their first measurements show that antimatter does have the same effect in gravity as antimatter does. Sorry, antimatter has the same effect that matter does.
Well, it works both ways, I guess.
Yeah.
I don't think we have time for any further questions on the live stream. However, if you're open to that, could we submit the rest of the questions to you asynchronously after the meeting? Would you be able to answer a couple of them?
Yeah, and if the YouTube video is public, I can also come and chat in the comments afterwards and answer some questions there.
Lovely. So we'll do just that. Thank you so much for your time. It was incredible to have you with us here. Should we do a final quick photo to end this?
Sure.
Some big smiles.
Oh wait, what do you want? Are you gonna have the background?
Yeah, sure. We can have your slide if you like.
You have this one.
Fantastic. Okay, got it. Thank you very much. It was incredible having you with us. More questions will be coming soon.
Excellent. Thank you so much for inviting me. Thank you for the excellent questions. They were really, really good. It was a joy to be here, and yeah, thank you for being interested in our work.
never-ending curiosity.
Yeah, exactly.
Thanks.
Preparation for live stream. You can also speak German, right?
And not really. One moment though, because I'm trying to find. Okay. I have to. So you have to turn on the sharing, I think.
The sharing.
Yes. So if I share my screen, it doesn't
Yes.
allow me. Okay. Now I can share.
Yay.
Okay. Can you see this? Or one moment. Let me.
Not yet.
Okay.
Yes.
Cool.
Irene has started screen sharing. Okay, but I don't see it yet. Is it coming? Are you sharing your screen?
Yeah.
Oh,
Now,
yeah.
yes. Okay. Cool.
Oh, yeah, I see it. Great.
Good.
Are we live? Oh no, there's one more minute. I think it's 3:29.
Okay. So it will be live in. Okay.
Wow, girls in quantum. Yay. Quantum mechanics. I'm so excited because this is also like a recapitulation of all that I have learned in university so far, because I'm starting my bachelor thesis very, very soon. And so this is so cool.
Nice.
Okay, is it streaming now? Live stream.
Mm,
Oh, okay. She said end. Okay, it's loading again. Preparation, Einrichten Ihres Meetings.